Hey, welcome! So today we're going to tackle a topic that, it often feels like the final boss in a calculus course. I'm talking about higher order linear differential equations. But don't sweat it, because we're about to unlock a seriously powerful technique for those times when the usual methods just, well, they don't cut it. You ready to level up? Let's jump right in. Okay, so here's our game plan. First, we're going to look at the problem itself. The kind of equation that just refuses to give you an easy answer. Then we'll introduce our master key, the power series method. From there, I'll walk you through the step-by-step blueprint, we'll see it in action with a couple of examples, and then finally, we'll get to the really cool part, the elegant solutions that pop out at the end.
All right, let's kick things off with a challenge. Why do we even need another method in our toolkit, right?
So you've probably spent a ton of time learning how to solve differential equations, but usually they have constant coefficients. Easy enough. But what happens when things get tricky? When you run into equations with variable coefficients, where you have a p of x in there. Well, all of a sudden, our standard go-to techniques can just completely fail. And that's where we hit a wall. We need something more powerful.
And that brings us to the solution. So when you're stuck, what do? You pull out the master key. And that key is the power series method. The whole method, the entire thing, is built on this one beautifully simple but incredibly powerful idea. We just assume that the solution, that function y we're hunting for, can be written out as an infinite polynomial. Think about that. We're basically guessing the form of the answer to help us find the answer itself. And you might be asking, why a polynomial? Well, because polynomials are the absolute easiest things to work with in calculus. You can differentiate them over and over and over, and they just stay polynomials. It's a brilliant bit of strategic laziness, and I love it.
Yeah, and this quote here from the source material, it really just says it all. When all else fails, the power series method remains a robust tool for any linear equation. This isn't some niche little trick. It's a reliable, heavy-duty tool. Doesn't matter how complicated the coefficients get, this method gives you a way forward. It's basically your mathematical safety net.
Okay, so we know what it is, but how does it actually work? Let's break down the process step by step. It's really just a systematic four-step process. Okay, step 1, we compute the derivatives of our power series. Step 2, we do a little bit of algebraic footwork to get all the powers of x to line up. Now this is crucial because it lets us find the recurrence relation, which is just a fancy name for a formula that connects all the coefficients in our series. And finally, step 4, we use that relation to actually build our solutions.
All right, that's enough theory. The best way to really get this stuff is to see it in action. So let's take this blueprint and see how it plays out with a couple of real equations. So let's start with a really simple case, almost a trivial one, the third derivative of y equals 0. Now look, you and I both know we could just integrate this thing 3 times and be done with it, right? But that's not the point. The point here is to prove that our big, powerful new method gives us the exact same correct result. It's like a sanity check.
And what do you know? It does. When you go through the steps, you plug the power series into the equation, and what you find is a rule that forces every single coefficient, every c sub n, to be 0 for any n that's 3 or bigger. So what are you left with? Just the first 3 terms, c0, c1x, and c2x squared. Just a simple quadratic polynomial, which is exactly the solution you get if you just integrate. Whew, the method works. Okay, warm-up's over. Now for the main event. Let's throw this method at a much more challenging equation, y triple prime minus y equals 0. This is what's called an Airy-like equation, and it's a classic example where the power series method really gets to show off. These kinds of equations are actually super important in physics. They pop up when you're describing things like wave diffraction and quantum mechanics. So we do the work. We substitute our series and its third derivative into the equation, we shift the indices around, and we get this. Now, this is the really cool part. We end up with a recurrence relation. This little formula right here, it might look simple, but it is the engine of our entire solution. It's telling us that any coefficient is completely determined by the coefficient that came 3 spots before it. So C3 depends on C0, C4 depends on C1, C5 on C2. You see the pattern? And here's the crucial takeaway, that one single rule, it generates 3 totally distinct and independent families of terms. The first solution, y1, is built completely from whatever we choose for c0. The second one, y2, is built from c1. And the third, y3, is built from C2. And think about it. It was a third-order equation, so we needed 3 independent solutions. And boom, the method delivered them perfectly.
Okay, this is pretty amazing, right? But we're kind of left with these infinite series. What do they actually represent? Let's zoom out for a second and look at the bigger picture here. I mean, we've done all this work, and we have these endless sums of terms. It can feel a little abstract, can it? So are these just some mathematical curiosities, or are they actually something, something real? And here is the beautiful reveal. It turns out that these 3 crazy-looking infinite series, they're just the power series for functions we already know and love. We're talking about the exponential function, e to the x, and a couple of its variations. How cool is that? It just brilliantly shows the elegance of this method. It took a really complex problem, broke it down into its simplest parts, and then used them to build a solution that was familiar all along.
Yeah, and this quote from the visual in the source material, it captures the practical side of this perfectly. It says we're approximating one of the basis solutions. Every partial sum of that series, taking the first few terms, then a dozen terms, then 100, each one is a better and better approximation of the real, true solution. You are literally building the function piece by piece.
So let's end on this thought. What the power series method really shows us is that even the most complex functions, the ones that solve these really difficult equations, can often be built from the absolute simplest pieces imaginable, just constants and powers of x. And that really makes you wonder, right? If these fundamental, simple building blocks can solve equations like this, what else can they build? What other complex structures out there, in math, in physics, in engineering, can they help us understand and construct?